So we finished the second order system when the system was underdamped, and for summarizing what we have done, when the um, f of s was 1, means impulse, we had this response, right? And we saw that the steady state error signal was 0. When f of s was a unit step 1 over s, we had this response, and we saw that ESS is 0. When we had f of s was ramp, we had this response. This is the input. Here we had the oscillation and this, and we saw that ESS was, for the second order system, 2 zeta over omega n. And when it was, the input to the system was parabolic, we saw that, in summary, this was the input, and we had the oscillation here, and we saw that ESS goes to infinity, increasing by time. Okay? To make it visible, let me see. This is the input to the system, and this is the output. Everybody understand? Yes? So now let's sorry. Let's move let's move when the system is critically damped. Means the zeta is 1. And I'm gonna consider two cases for the impulse and the tell me and the step. But then I'm gonna just extend my result to these two and go to mathematics simulating and visualize. So when the f of s, again, when it is impulse, okay, so x, remember x over f was omega n square over s square plus 2 zeta omega ns plus omega n square. When zeta is 1, you can write that the x, because f is 1, this is omega n square s square plus 2 omega ns plus omega n square. And remember that for critically damped system, we had two repeated poles. Poles what P1 and 2 we have in your notes was minus zeta omega. Meaning that in the complex plane, the real and the imaginary, we had two real poles on each other. Right? Here is zeta omega. Having that, you can write this as this: omega n square s plus zeta plus, because zeta is 1, plus omega n square, because zeta is 1, that's right. So it's gonna be minus omega n, two repeated poles, right, from high school. Now you have to decompose this as a over s plus omega n square plus b over s plus omega n, because it's a second order. I'm intentionally do it because I'm gonna show that there's no need that you do it. If you do this, guys, I bet that you'd get B0. Please do it as homework at home. You don't do that. Please do it and prove it to yourself. B gonna be 0. So you're going to get again A. So obviously from here you get that the A is omega n square. So the question is, can I go to next page? Yes. So question is, when x is omega n square over s plus omega n square. Now we're going to go to the time. What I have to do? Laplace inverse. So which function Laplace is this? I'll give you 1 minute that you think about this. Go to your table of the Laplace like I told you. So remember that Laplace of guys t, remember, was 1 over s squared. And I told you that Laplace of, remember, e minus at, you have in your notes, f of t is f Laplace s plus a. Remember? You have in your notes. So when you see s squared shows this, but this a is this a. So on the other hand, x of t gonna be omega n squared is here out. So you're gonna have e minus omega nt, and your f of t gonna be this in t. Everyone understand what I have done? So you're gonna be omega n squared t e minus omega nt. Here we go. So we plot that. We got the answer. When your system is critically damped and the input is impulse. So if I want to plot it, t and x. Again, this is input, impulse. So obviously, guys, all of you look at here. When the system was underdamped, your response was this. A constant number, e minus zeta omega nt at this part, sine omega dt. That's right. Sine omega dt. So it has a transient harmonic and then decaying. Do you see any transient harmonic term here? Do you see that? No. So that's why the output of the system gonna be like this. There we go. Understand what happened? So there is no oscillation when the system is critically damped. Comparing this with the underdamped system, gonna be like this. This is underdamped system. So on the other hand, there is no, and the system acts like first order system. There is no oscillation for critically damped second order system. Everybody understand? Yes? Yes, guys? Good. And nothing changed. Obviously, you see that even that there is no oscillation, what is the steady state error signal? What's the steady state error signal for the impulse? Output follows the input. What is that? Zero, exactly. Nothing changed. Can I go to the next page? So, even if, for example, if you try the final value theorem, 1 plus g, when s goes to 0, f is 1, impulse, s, 1 plus g, again look at your notes, it's open loop, s in s square plus 2 omega n, because zeta is 1, that's right, critically damped system. It's going to be 0, because we have s here. Clear, everybody? Yes? So, now let's go to the second case of that. When the zeta is 1 critically damped system, and your input to the system is a step 1 over s. This is for a step. We did with the impulse. So again, x over f is omega n square s square plus 2 omega ns plus omega n square. So from here you get that the x, because this is 1 over s, 1 over s omega n square, again s plus omega n square, because you have a pair of you have two repeated real poles for critically damped system. Again, what you're gonna do, you're gonna write this as this time. A over s plus omega n square plus b s plus omega n plus c over s, because we have two repeated poles, we have to write like this. But despite the previous case, b is not 0. You have to calculate. So you can write it as this: s in s plus omega n square. You have as here plus bs in s plus omega n plus c in s plus omega n square. This is equal to how much? Omega n square. So you get the denominator equals to omega n square. So now you can arrange that based on s. So you have one s square here. You're gonna have b. One square here. You have c in s square. Okay. You have one s here, a plus b omega n. 2b omega n here. No, b omega n. B omega n here, see? And you have plus 2c omega n at s, right? And the only constant number you have is plus c omega n square equals to omega n square. Let me double check everything, okay? Because I'm developing with b plus c plus a plus b omega n plus 2 omega n c. Yeah. So from here, you get the only constant number c is 1. Bingo. If you implement it here, you get b is minus 1. Bingo. And if you implement all here, you get a equals to minus omega n plus omega n. 2 omega n. Gonna be omega n. Here we go. No, this is wrong. B S omega, so 2 S. Oh, minus. Very good. Yeah. Minus. Let me write like this. Minus B omega n minus 2C omega n. So it's gonna be omega n minus 2 omega n. Gonna be minus omega n, not plus omega. Okay. Okay. So, can I go to the next page? Yes, everybody? Being said, your x of s gonna be, how much is that? Minus omega n. I'm gonna move everything here. C is 1. 1 over s. 1 over s. Your b is minus 1. Minus 1 over s plus omega n. And the a is minus omega n. Minus omega n in s plus omega n squared. Now you can have the inverse Laplace. So you get the x of t. This is obviously is the input to the system. Step. This is exponential term minus omega n t. And as we did today in the previous case, it's gonna be omega n e minus zeta omega n t in t. So you can write like this. Step minus e omega n t. Again, step because this is 1 plus t omega n. Here we go. So if you plot it, x t, and this is input to the system. At t0, this is 0, this is gonna be 1, 1 minus 1, 0. X is gonna be this. Here we go. At t infinity, this goes to 0, and x gonna be How much? 1. That's right. X gonna be unit step. But what's the difference between this case and when the underdamped system? Remember that the x of t for underdamped system, we have in your notes now, was e minus zeta omega nt, remember? Cosine omega dt plus, actually 1 minus this. Let me fix this, guys. X was 1 minus this plus zeta, I taught you having what's sine omega dt. In the transient term, we had what? Harmonic. But here, we have no harmonic term. So again, for critically damped system, you never have oscillation. This goes like this. Like as the first order system. For critically damped system, there is no oscillation for second order system. So this is for zeta is smaller than 1, and previously I taught you that this is for zeta smaller than 1 for underdamped system. Clear, everybody? Yes? So we are not blind. What's the steady state error signal for the even under oh, sorry guys, this is a what's the steady state error signal for critically damped system again? Huh? How much is that? 0. Nothing changed. Okay? Nothing changed. Are we done in this page? Yep. So, having this, now I can move for critically damped system without doing the calculations. And f of s is ramp. This is for ramp. X over f again is omega n square in s plus omega n square, and your x gonna be 1 over s square omega n square s plus omega n square. So here, when you have the fractional, this is going to be a over s square plus b over s plus c over s plus omega n square plus d over s plus omega n. Now, before we do calculations, we know that because system is critically damped system, will we have oscillation or will not? Do we will have oscillation? Yes? Hello? Everybody? Disconnected? Oh, I have to cut it, huh? Oh, okay. So I think that you slept, all of you. So we will have oscillation or not? Okay. So because system is critically damped. So having that, you're gonna have this again. S square S plus omega n square. You're gonna have A in S plus omega n square plus bs in s plus omega n square plus cs this plus ds in s plus omega n. So obviously this equals to omega n squared. So now you can sort based on the order of s. S cube. S cube, you're gonna have b1 here. That's it. It's too much space. Let me see. Yeah, you're gonna have b s cube plus a plus 2b omega n plus c plus d in s square plus 2a omega n plus b omega n square plus d omega n in s and plus a omega n square equals to omega n square. Okay, let me double check, guys. Only this is b a plus 2b omega n plus c plus d s 2a omega n plus b omega n square plus d omega n. Yes. So from here, obviously you get a is 1. From here you get b is how much? 0. So from here you get, because b is 0, a is 1, you get 2a omega n minus, gonna be d omega n. A is 1, this with this goes to hell, it's gonna be minus 2. Okay? So from here you get C gonna be minus A minus D. A is minus 1, D is minus plus 2. Gonna be 1. Bingo. Okay? Everybody? So, having that, x is gonna be 1 over s squared c plus c I see there is a mistake here. That's why I'm saying, because I'm driving with you. Okay. So that's why everything here is wrong, guys. I always double check even myself because I'm driving with you. See? I'm glad that I didn't go ahead. Okay, so we have ds squared. Okay. So we have a d here because I was thinking oy. D plus b. Here we go. So if that's the case, obviously I have to calculate. So from here, a is 1. Okay. A is 1. From here, b is equal to minus d. Okay. Now what we have from here is this. Look at here, guys. So there's lots of things to change. S square. Oh, hold on. So a. Okay, d gonna be there. D gonna be, oh, you have to multiply by omega in here. Let me fix this, guys. It's gonna be d omega n. Now it's right. And we're gonna remove from here because we don't need that. Because we increase that. Yes. Now it's right. So a is 1. That's right, from here. From here. From here. You get b. You get yeah, b gonna be let me double check everything, guys. B d, that's right, s cubed, s squared gonna be a plus b 2 omega n plus c plus d omega n, right? Now 2a omega n plus b omega n squared. There's no s. Okay, wait. Okay. So from here, your b is b omega n squared is minus 2a omega n. So your b gonna be minus 2 over omega n. Okay. So from here, your d gonna be minus b. So you get 2 over omega n. Okay. And from here, so your a is 1. Your b is minus 4, and omega with omega n goes, plus c and plus 2 is 0 because this omega n with this omega n goes. So you get from here c equals to 3 minus 4 is C gonna be 1. We calculate everything. Now these are the constants. So can I go to next page? Good. So you get x of s gonna be 1 over s square. Your b minus 2 over omega n s minus 2 over omega n s what is the c? Oh, c is 1 plus 1 over s plus omega n square, and your d is 2 over omega plus t over 2 over omega n s plus omega n. Now it's simple to find x of t. So x of t gonna be input ramp minus 2 over omega n. Here we go. And this is valid, guys. Why? Because I taught you when the system is under damped, steady state error signal was how much? You have in your notes. 2 zeta over omega n. Now your zeta is 1. Do you see it here? Yes, you see it here. Plus t e minus omega n t, as we did in the impulse, plus 2 over omega n e minus omega n t. Okay, so you can write that x of t equals to t minus 2 zeta omega n impulse, because it's 1, plus e minus omega n t can factor out, 2 over omega n plus t. Obviously, despite the case of underdamped system, there is no oscillation here because there is no harmonic term. And the input output minus input means steady state, means error signal is this 2 over zeta omega n plus e minus omega nt 2 over omega n plus t. Meaning, mathematically, ESS, steady state, means t goes to infinity. When t goes to infinity, this goes to how much? 0. Gonna be as we had and we developed previously, like this. 2 over omega n, because zeta is 1. So a steady state error signal of this system is the same with the underdamped system, with the exception that the zeta is 1. Right? So if you are done, I will move to the next page. Can I? So if I want to plot it, we'll go to Simulink and we're going to do this, okay? Hopefully next class. So x t is the input to the system. For the underdamped system, we have the oscillation here, as you saw in the MATLAB Simulink, and then steady state error signal. This was for zeta under them. But for here we don't have this. We're gonna have this. There's no oscillation here in the transient response. This green is for zeta 1. But the steady state error signal is the same, E. The difference is this transient response. Clear? So, being said, let me finish it when we are in the critically dynamic system and the f of s is parabolic. Again, your x of s is gonna be 1 over s cubed omega n square in s plus omega n square. Please do it as homework at the home. I don't want to spend your time here. It's gonna be the same process, except that we're gonna have more coefficients. 1 over s cubed plus b over s square plus c over s plus d over s plus omega n square plus e over s plus omega n. Please do it homework. Okay. Find the a, b, c, d, f. Okay. So you're gonna see that at the end, your x of t gonna be in this format: parabolic minus a constant. Let me change the constant. Say c1t plus c2 plus, again, e minus zeta omega n. Oh, there's no zeta. Zeta is 1. Okay. Omega nt. Here, I don't know, a constant c3 plus c4 in t. Okay. I assign you that you do this, and that's homework. Just gonna kill your time if I double it here. Okay. So you see that when time goes to infinity again, this goes to 0 because of this decaying term. Input minus output, as for the underdamped system, goes to infinity because time increasing. So the error signal of the system, like as the underdamped case, goes to infinity. Okay. The only difference is that for underdamped system we have oscillation in transient response, but here we don't have. Okay, here. Oh, what happened? Come on. Here. What happened? Oh goodness. I have to wait. There's some malfunction in PowerPoint. Okay, finally. Here, there is no harmonic term. So if I go to the next page, if I plot this, x over t, this is the input of the system, parabolic. In the underdamped system, we had this oscillation here, but here we don't have that. We have this There's no oscillation. Understand? So again, like as the underdamped case, nothing changes. For the critically damped system, steady stereo signal. For delta, for unit step, for ramp, for parabolic. 0, 0, 2 over omega n, because zeta is 1, and infinity. That's it. The same. Remember, for underdamped system was the same. Only that zeta we had here, but here zeta is 1. There we go. Okay, guys. Next class, I'm gonna simulate this in MATLAB and Simulink, and then we go for the overdamped system. I'm gonna make the overdamped system very short because it's gonna be the same process, but we have to make a little different conclusions. Okay? Thank you, guys. If you have any question, I'm done.